record the screen. Did you see the slide?
Yes, sir.
Yes, sir.
Okay. So this much we discussed in the last class, that there is a two type of pressure vessel, thin wall and thick wall pressure vessel. So if there is a two type of pressure vessel, obviously there will be two different formula, one for thick wall and other one for thin wall. But in undergraduate level, normally we teach thin wall. Thick wall is little bit bigger equation, you have to derive the equation in different way, and normally they teach in masters. I don't see any thick wall pressure vessel they teach you in the undergraduate level. So in this course, we learn about only thin wall pressure vessel. So this one will keep you textbook. But still, we need to know that you need to have a scale, how to measure that a pressure vessel is thin wall or thick wall. It don't mean that only the wall is thick, then you can say this is thick wall. Wall is thin, you can say this is thin wall. Even your birthday balloon is bigger size, this is what behave like a thin wall. But same wall thickness, if you make a smaller pressure vessel, that might work like a thick wall pressure vessel. So what is the tool to figure out how pressure vessel is thin and thick wall? There is a one standard rule that if Ri, internal radius of the tank, is less than 10 times of wall thickness, then we will call it a thick wall pressure vessel. And if the wall thickness is equal or greater than 10 TW, then you can say that is thin wall pressure vessel. It should not be K over here. Okay. Now, this is based on the wall thickness and radius. Other pressure vessel based on the geometry is like cylindrical, spherical, then close and open pressure vessel. Seems like, for example, you are carrying high pressure gas from Kumula to Dhaka. So what actually happened? Both end is open, but they behave like a closed end. You delivering gas from Kumula to Dhaka, but in the middle somewhere, North India, somewhere your pipe got exploded. How come? That means inside pressure is getting very high, or your metal is very weak and it's burst. Okay. So those are the type, but we'll use. Sometimes you will see that even you have a open pressure vessel, but is behaving like a closed pressure vessel. Okay. Now we need to know that how a pressure vessel fails. What are the reason, or what are the stress inside? So a pressure vessel normally experience three type of stress. Number one is sigma T. With the name, you can say is not the tensile. It's tensile stress, but it is called tangential stress. Sometimes some book say it is hoop stress. And sometimes you go for job interview, they will ask you, could you write the hoop stress of the pressure vessel? And I see a lot of people, they don't know what the hoop stress. But hoop stress, tangential stress, they have other name. It's called circumferential stress or peripheral stress. Both have the same name, sigma T. Then one stress is called radial stress, sigma R. Then longitudinal stress, sigma M. So those three type of stress is what in the pressure vessel. Okay. So if any of these three stress become higher than the ultimate or yield strength, that means your pressure vessel is failed. Now, how will you measure this stress? Say you buy a pressure vessel or gas cylinder for your car. Now, how much pressure will be inside? 400 psi or 300 psi? What will be the stress? There is no tool to measure the stress except you put the strain gauge. So we need to have a formula to derive those three stresses: sigma T, sigma R, and sigma L. Before we derive the formula, Right now, you just know this is hoop stress, radial stress, longitudinal stress. But what physically, what does it mean? What is the effect and how it is actually coming those stress in a pressure vessel? So that you need to understand. And to explain that, uh, if we look in this figure, what is showing this figure? Say you are taking a bigger plate, say 3-inch thickness of this plate. Say if I try to show you the thickness of the plate straight, is going like that. Okay, so 3-inch thick plate. In that plate, you make a hole. So what I'm saying, this thickness is I'm not able to draw the straight line, but thickness remember 3-inch or might be 4-inch. Now you make a hole. Say hole diameter D equal to 3.0 inch. Now you like to put a bush or you like to put a shaft, but shaft diameter ds equal to 3.005 inch. So what do you think? It will go automatically inside the shaft? Obviously not. There is some interference, right? So what will you do? You just put it over there, then you can hammer it a little bit, then it will go inside. But this interference, I put 0.005, but it might be 0.01. So depends on the how much interference, the hole, what is the length of the hole? Obviously 3-inch, right? Because I said that this thickness of this plate is 3-inch. So length of the hole will be 3-inch. And your shaft might be say 5-inch long or might be 4-inch. You are just putting in the hole, and then the other side you are hammering with the hammer little bit and try to insert that bush or shaft within the hole. Then you need to realize that what kind of things might be happen there. Number one, things might be happen that if the material of the plate is a little bit softer than the shaft, then what will happen? This diameter of the shaft might be increased, and it will let the shaft inside the hole, right? So in that case, diameter will increase. How it will increase? That means somebody pushing along radial direction, right? Otherwise it should not increase. So if radial direction somebody pushing by some force, that means there is some stress. That stress work radially, and it is designated by sigma r. That's the radial stress. Okay, this is one possibility. What is the other possibility? That when you hammering, yes, your hole is getting a little bit bigger and shaft already inside 3-inch, but suddenly you see the right over here crack develop in the metal. What is the crack? Crack means the gap between the material. It's not a gap, right? Might be your gap might be point like 0.002 inch, or might be less than that. Might be kind of like a hair thickness, but still there is a gap. Now, before there was no gap. Now, how gap is coming over here? Obviously, somebody is pulling this portion along this direction, and somebody pulling this portion along this direction. That's why it becomes the gap. And you see, pulling this direction, it actually working along tangent of the hole. That means tangent of your cylinder. That means your hole, right? So this stress is called sigma T. This is called tangential stress or peripheral stress. Is always work along the wall of the pressure vessel, tangential. Okay, that is called sigma T. This is one possibility. What is the other possibility? There is no crack developed, the hole get a little bit bigger, then it might happen that this plate is 3-inch and it become 2 plate. How? One plate thickness become 1 inch and 1 inch, other become 2 inch. That means if I draw this case, that your total length was 3 inch of this hole, but some reason it become 2 part. That will right over here become 2 part. Why 2 part become? Is not, it will not become 2 part automatically, right? That means somebody push it along this direction, somebody push it along this direction, and become 2 part. That means this stress, this somebody pulling by a force by area, that means stress. So this is happening, somebody pulling along longitudinal direction, along length of the pressure vessel. So this stress, we can call it or give a name, that longitudinal stress sigma L. Okay, so same thing happened in the pressure vessel. I just give you an example with a hole and shaft. But obviously, when you put a oversized shaft in a hole, then the hole experience pressure like pressure vessel. Okay. Now you see there is some diagram over here. So what I did in this diagram, right over here some material, right? So at a angle theta from the x-axis, I make a angle d theta, and this material I took this portion, and obviously you see from here to here you have 1 radius, then from here to here you have 1 radius, right? Then this portion have some thickness, and I like to figure out that what type of stress might be there. So obviously there will be stress along radial direction. That means the radial stress try to make the diameter of the hole bigger. That means there is sigma r will work along this direction. Okay, 1 second. So you see this is sigma r with red letter. So this is a static body. That means in solid mechanics we are working with a static body. So right over here, this body is working. So this is sigma r. So in other direction, will work also sigma r. Then it will be static, it will no movement. If this direction works sigma t, sigma they put sigma theta and sigma t is the same thing. Some book write down sigma theta as a tangential stress, some book directly write down sigma t. So along this direction, if work sigma theta, obviously along this direction there will work sigma theta. Okay. Now, how the material will, fade. So if I take a similar chunk of material, right over here, I'm saying this is outer peripheral area, this inner peripheral area, I'm connecting with this. Okay. Then this angle with the center will be d theta. Now in that case, force will be along trace sigma theta or sigma t, tangential direction. And along this direction will be sigma r, this direction will be sigma r. So what is the possibility that due to the sigma theta, material might be generate a crack along this direction due to the sigma t, because both are pulling in tangential direction. Other thing, there might be developed a sigma r along this direction, sigma r along this direction, and due to the sigma r, it might crack along this direction. Okay. So when you design a pressure vessel, you need to figure out all the stresses, sigma t, sigma r, and sigma l. Sigma l I am not showing over here. Then you figure out which one is higher. If any of these stress becoming higher than yield strength of the material, then your cylinder will be fail. If it become higher than ultimate strength, automatically it will burst after within few seconds because you load it with higher strength, or it might be burst within 10 minutes, or depends on what is the pressure, what type of pressure vessel, and what material you are using. Okay. So to design a special vessel, why actually we need to analyze the pressure vessel? Because you look at the what are the equipment used behave like a pressure vessel. For example, airplane, submarine, boiler. We use gas in our home, also in our car. Lot of companies they carry the gas in a cylindrical shaped container through a truck or might be by through train. Then lot of chemical industry, nuclear power plant, they use pressure vessel boiler. So we need to make sure there will be no explosion of those boiler, there will be no damage of the property, and there is no harm in the people's life. So whatever you making, you need to make sure that those are safe to use. So that's why we need to analyze or design the pressure vessel, that whatever material you are using, that material is safe to carry the pressure load. Now you see right this figure, a longitudinal stress, sigma L working along this direction. Okay, along this direction. And this is sigma T, right over here, tangential direction. And sigma R, this pressure pushing upward, and there is a outside resistance working downward. Okay, so you see due to the longitudinal stress, this might be generated crack right over here. But that means it becomes too far. And due to the tangential stress or hoop stress, this one might be become make a crack like that. And for radial stress, it might be radius either increase or might be decrease. And pressure vessel, you might see the only it has a inside pressure is higher. That is not true. Sometimes outside pressure might be higher. For example, kind of submarine. In submarine, under the bottom of sea, inside they maintain pressure about same as atmospheric pressure because human life is there. We feel comfort at which pressure? At 1 atmospheric pressure. You know, a lot of people have heart disease, and you like to climb up a hill in a national park, and you will see there is a sign that if you have heart disease, don't go there. Because at top of the hill, your pressure is low. But inside your human body, pressure is 14.7. So your heart might be don't work at lower outside pressure. So that's why they'll say, no, don't go there. If you have a heart disease or if you have extremely scare feeling. So in submarine, you see inside pressure is atmospheric pressure. So how much pressure will be outside? Outside pressure will be like pressure of the fluid pressure. Depth depends on how much depth is in the sea, because P equal to H rho G. Similarly, in some chemical industry, say you have a cylindrical tube. Outside there is a one tube. Inside there might be flowing very low pressure fluid flowing along this direction, but outside might be a high pressure fluid going along this direction. So this fluid pressure also works right over here. So it depends. So it don't mean that your pressure vessel have pressure only inside. There might be pressure outside too. That's why when you have birthday balloon and you put air in the balloon and the volume getting bigger, and you then tie down your mouth of the balloon. So keep it open. What will happen? It is squeezed. Why? Because it inside has a low pressure, but atmospheric pressure is pushing him. Hey guy, don't expand. So ultimately, to the outside pressure, the air is getting out from the mouth, and finally it is gets squeezed. Okay. So just to give you idea that how those three stages work, how we can estimate. Again, right over here. Now, I'd like to say one thing, that if pressure vessel is thin wall, we got three stress, right? One is sigma T. Sigma T means tangential stress. We got sigma L, longitudinal stress. Other one we got sigma R, radial stress. But normally, if pressure vessel is a thin wall, then sigma R and sigma T is almost same. Or sigma R we can, because wall thickness is very low, so sigma R become equal to the sigma T. That's why there are only two stress wall. One is sigma L, other one is sigma T. But if it's thick wall pressure vessel, then you need to figure out all those three. Okay. Now, how those things you can measure? Obviously, you need to have a formula, right? So how we can derive that formula? You see in the right over here, this is a cross section of this cylindrical pressure vessel. Inside pressure is working, and pressure always work perpendicular to the surface, like perpendicular to the surface. Okay. So I take the half. Say you try to look for first half of the pressure vessel, only this part. Okay, then what you see? I like to see that this is center. Say this is pressure or pressure force work. Similarly, if this angle is theta, I'm saying this angle theta or say 20 degree x-axis. So similarly, from right over here, there will be one more force work along this direction, pressure force, and say angle 20 degree. So these two forces has to be equal because cross section is symmetric. Angle you took the same. Now, if angle is 20 or theta, then this F you can make two components. You can make one horizontal component, F cos theta. You can make one vertical component, F sin theta, right? If this angle is theta, then this will be F cos theta. 1 second, my mouse pad is not working. So this will be F cos theta. And vertical direction, it will be F sin theta. Similarly, if I break this one, there are two components. One will be horizontal component. This will be similarly F cos theta. And vertical component, right over here, that will be F sin theta. Now you see the horizontal component, both are same but working in opposite direction. What does it mean? It cancel out. So only you have remain in radial direction. F sin theta is making your cylinder is fast or fade because the horizontal component is already cancel out by each other. So if I take a half of the cylinder, if I take the length is L, if take the whole view, then along this side there is a thickness, right? Along this side, if I take a green color, if all thickness is T, so there will be thickness right over here, right? This thickness at the bottom. So what will be the area of this thickness? This thickness, what is the area? If all thickness is T, then this area will be T times L. Similarly, you see right over here, thickness is sigma T showing over here, but this sigma T is working everywhere, right over here for the thickness. Right over here also working sigma. So right over here, your area will be also T wall thickness into L. So you have area. So how much force is working? You see for this half, it's showing thickness of the wall is T. and inside pressure is P. So all of the force, the horizontal component will be cancelled out from left side to right side. So only you have vertical component, all the vertical component working along this direction, right? Along this direction. This vertical component working along this direction. So this vertical component has to be balanced by a resistance of the material that working down. So that one we saying sigma T. This is sigma T, this is sigma T. So both sigma T working downward, right? With which area? With T into L, right over here, T into L. So the force working downward, that one how much? If I take summation, it will be 2 into sigma T into area. What is my area? T into L. This much force working downward. Now you see some pressure force working upward. So how will you get the force? That pressure force. We know the force equal to pressure force or pressure into area. So if you figure out all the area of this, all the area, then you can figure out this force working in vertical direction. And this one I can say force working in downward direction, FD. Then you can say FD equal to FD. But you need to figure out, right, this force P into area. This amount how we can figure out. So that we will derive a formula. And right over here, they are just trying to show a chunk of material. This is sigma L working along this direction. This is sigma L along this direction working sigma T, along this direction working sigma T. Let's just try to show that how sigma T and sigma L is working here. Okay. Now our next target will be how we can measure the sigma T, and also you have to look what will be the failure due to the sigma L and due to the sigma T. So if their sigma T L war, due to the sigma T L is called longitudinal stress. That means somebody pulling this along this direction, along this direction. So finally it become 2 parts. That means one boiler become 2 boiler, on a pipe become 2 pipe. Now what will be the failure due to tangential stress? Due to the tangential stress, along your pipe or cylinder just become 2 half. 2 half in, that means upper half, this one and this one. This one is still workable, right? It become breakdown in along the length, but still it is like you can take it, you can use it. But you look in the upper one, it's complete failure, just burst. That means that upper part will fly along upward direction and bottom part will fly along bottom direction. So normally pressure vessel is failed due to this sigma T, and you will see mathematically that sigma T is very dangerous for the pressure. So we need to derive a formula that how we can figure out the sigma T. So let's see what we have in the next slide. In the next slide, you'll see we'll derive the formula for sigma T and sigma L. So how we can derive? We are considering a thin wall pressure vessel. We are at the beginning, we are this assumption we are making. So whatever formula we'll get, we'll describe it as a just 1 second, just one more. Sorry. So we are thinking that we are taking a thin wall pressure vessel. That means whatever formula we get from the derivation only applicable for thin wall pressure vessel. We are thinking that both end is close and subject to uniform pressure P. and length of the cylinder is L, wall thickness T, and radius of the cylinder is R. Now this is your loading assumption and geometry of the pressure vessel. Then you need to make some assumption about the material, what type of material. We are saying homogeneous material. Material is isotropic and of a Hooke's law. Just hold on 1 second. I'm getting some noise from my neighbor. Okay, some construction is going on. That's noise. Okay. So what I'm like to say, those are the assumption is about the material, and those assumption almost same when you derive a beam, when you derive a column, or when you derive the equation for the torsional shear stress. And because it is a thin wall, we are thinking that thin wall have two stress, circumtangential or circumferential, or hoop stress, the same one. Okay. Then longitudinal stress sigma L. Now it's saying free body in the next slide. So let's see the free body of the pressure vessel. So we took the half of the pressure vessel. So you see all the pressure. I already show you that a component of the pressure force in the horizontal component will be cancelled out by each other. That means these two pressure force I draw as a right hand, this will be cancelled, but their vertical component will be remain working upward, right? So this vertical force has to balance throughout the thickness and throughout the length. So force working in downward direction will be how much? If I say this is minus, trace equal to force equal to trace into area, right? Trace into area. So how much, right? Throughout the thickness, trace working sigma T. So what is the area? Area will be thickness of the wall T into L. This is area. This area you multiply by sigma T. This much force working downward in one side, this side. So how to be the right side? Same. So we just multiply by 2. So this much force we are getting working in downward. Now, how much force working in upward direction? That we need to figure out. So in upward direction, we have pressure we know. So we need the area. So we need to figure out pressure into area. Then we get the force. How we can figure out that force? You see, we took a small portion of from the thickness area. This portion is, and we are thinking with the horizontal axis and this line make an angle theta. This angle is theta, and this point and this point make angle d theta with the center of the cylinder. Then we can figure out the small length light over here. What we took actually, we took a chunk of material in this shape, right? And this material is going throughout the length, is stripped with. So what will be the length of this portion from here to here? Because all the pressure force is working right over here. Right, this is outside. So we need to figure out this area, this length. This length you can figure out. How this length you can figure out? Angle is theta. This one make angle d theta with the center, and radius is r. So your this length from here to here will be d theta into r. This will be length. And So how much the total area? That we need to figure out. So from this figure, you might be a little bit confused, might be don't understand, but if we look the next slide, right over here, that means this portion, this is front view, but this portion, you are taking all the way throughout the length of the pressure vessel. That means you say this is the center, this is the center. Okay. So this angle, this mass angle is d theta. And you know this length r into d theta. This length is going throughout the length of the your pressure vessel. That means I took a small segment, longitudinal segment from the pressure vessel. If I say I took this segment, this line, so this line right over here, I connect this line, and these two make angle d theta. So I am talking about this segment, and this segment has a length L and thickness T, but outside no pressure, only inside this side, this portion is experiencing pressure. So I got this length d theta into r, and total length is L. So the area will be d theta into r into L. So if we look in the next slide, that I mentioned it right over here. Say this portion, that means this chunk of material, if I take the blue color, that means from here to here, what will be the length from here to here? This length will be this one, r into d theta, arc length. Then this area I need to meet. You see the arc, but this area is kind of along the length of the cylinder. So inside this area, you need to come. So you got this length, and this length is width, you got r d theta, and L is length is you have. So width into length, that is the area. So area will be length into width, that means L into r d theta, that will be area. Okay. If that is the area, then what will be the force? Area into pressure. So my pressure is P. So P into LR into theta. This is the force working in this right over here. This is dF right over here. This P into dA. And we got the A, LR d theta. And this is what we'll take only vertical component, because if you took the similar segment right over here, you will have a horizontal component. And this component will be cancelled out. Horizontal component dF is F cos theta, vertical F sin theta. So F sin theta, we need to deal with this F sin theta. So this dF is working only right over here, right on the small segment. So how I can get vertical force cover all the side from angle 0 to theta, 0 to 180. So if I vary this d theta from 0 to 180 all the way, then I can get summation of all the vertical force. So small vertical force PLR d theta, this is the area, into P, then multiply by sin theta. So that force working in vertical direction. Now the horizontal vertical force working downward direction, that I already show you in the previous slide, right over here. This one. So you see that PR sin theta L dl, that one right over here. PLR d theta sin theta. So same thing we put PR d theta L sin theta. And we're integrating 0 to pi. Then PLR, you take it out. You will have only inside the integration 0 to pi sin theta d theta. Then you integrate, then you will get the tangential stress. this sigma T equal to PR by T. So right over here, okay, right over here we elaborate more that while the sigma T working, right? All the pressure force working in this surface, working like along this direction, and your sigma T working through this area. So what will be the force? What will be this area? Stop this area. This area will be thickness into F, right? T into F. That we put it over here. So by deriving this formula, we can figure out the tangential stress in the pressure vessel. That I just show it again over here. The how figure out the DF equal to this, and then you say summation of DF equal to 0. This is downward force working through the thickness at the wall thickness. 2 into sigma T, L is the length, T is the thickness of the wall. Then you see R into the theta is the width of the strip into L, that is the area. You multiply by the P, you get force, and you add sine theta into the vertical component. Then you just do the integration and simplify. Finally, we get this equation. Sigma T equal to PR by T. Now, this PR you can express in terms of diameter of the pressure vessel. So, PR will be PD into 2T. You just multiply by 2 at the top and the bottom. 2 are equal to D, then you will get this equation. Okay. So, this is very simple. Anyone has any question?
Sir, is the force acting here a summation of internal pressure and the tension throughout the walls?
What to say?
Is the force acting here, which we can see here, is it the summation of the internal pressure and total tension in the walls?
Yeah. Hold on. I let me turn on the video. I show you something. Actually, I am out of Dhaka, for my personal reason. That's why it might be able to see clearly. 1 second. Did you see a notebook, right? You see, I just bend it like that. If you look in the video, I bend
yes, sir.
So pressure working inside. I'm showing with my finger, right? And it have two components.
Yes, sir.
Horizontal, other one vertical. The horizontal component will be cancelled out by left side and right side. But vertical component will hit the wall, right? I'm just hitting with my finger. And that will be resist by sigma T through this wall downward. So say what this area. Area will be thickness of this my paper, this notebook, and then this area. Similarly, you have area right in this side, and also this side. So these two area, this one, this area, and this area will resist. So that area is I put right over here. This is the area. You multiply by sigma T working downward. And right over here, what I took a angle, some segment, some strip, like you cut with a blade. And then you say how much force is there, and you take only vertical component because you know that horizontal component will be cancelled out. You understand now?
Yes, sir. It's clear now.
Anyone? You scared? No, you should not be scared. You just read one more time. It's very simple. If this one you scared, then you don't see the thick wall pressure vessel. It's more complex than this one. And you have to derive by using cylindrical coordinate, not the. We are deriving not the cylindrical, but there is a lot of big derivation. Okay, thick wall pressure. So this is tangential stress, and you have to derive one more stress. That one is called longitudinal stress. So longitudinal stress, actually, what happened? Due to the longitudinal stress, your pressure vessel just become two part, right? Just crack right over here. How crack develop? That means somebody is pulling along this direction, somebody pulling along this direction, right? So this is the sigma L we need to know, because sigma L make the pressure cylinder into two parts. Now this sigma L, how we can derive? Say this is the half of pressure vessel, right? So if you took half, you see at the wall, pressure is hitting left side, right side, top, bottom. What will happen? That will be cancel out each other, right? In every angle, they will be cancelled out. But at the cap, if cap area is A, how much is force working along left direction? P into A, force into area, right? And what is this area? From here to here, how much the radius? Radius of the cylinder. So P into pi r square, that much force working along this direction, left direction. So what I did, we tried to take summation of the force along length of the cylinder. So along left direction working force PR square. And how it is resisting? By a cylindrical strip at the outer area, right? So what is this area? Length will be 2 pi r, and if you multiply by thickness T, that will be area, 2 pi r T. And multiply by stress, you will get the force. So minus P r square plus 2 P r T into sigma L equal to 0. Then just simplify, you will get sigma L. Sigma L equal to P r by 2T. So you see, we are getting two formula. We are getting sigma T equal to P r by T. And sigma L equal to how much? Sigma L equal to PR by 2T. So which one is bigger? Anyone? Anyone could be?
Tangential one.
Sigma T,
Tangential
right?
one.
Sigma T
Yes,
is
sir.
Yes, sir.
so that means if your pressure vessel is survived by sigma T, then you don't need to worry about the sigma L. If sigma T coming 40 psi or 40 ksi, your sigma L will be 80 psi. Okay, double. Now, if I try to show you that how sigma L is resist, say this is, I make the pressure vessel with the node, okay, cylinder. So sigma L is working along this direction. So if you just take this area, what will this area cut it? There will be this length, right? So what will this is? Kind of rectangular with the thickness, you see. So this is will be length will be how much? 2 pi r is the length into wall thickness T. So that we did over here. Okay. And if end is close, this end, I cover it my hand, how much force I will feel? Inside pressure into this area of this circle, pi r square. That we put it over here. So in the exam, and 2 pi r, if you want, you can express in terms of D, because both one you multiply by sigma L, 2r, if you multiply by 2, then you get P into D divided by 4T. That will be your sigma. You can express in terms of T, D diameter, or you can express in terms of radius. But result will be the same. So we can keep it over here. So any question that you need to, I need to explain, or you have confusion. Any question? No?
No, no, sir.
Okay.
Sir, one question.
Yeah, sure.
Sir, এই যে ফ্লুইড যখন ধরে নিলাম যে একটা ট্যাঙ্কার যেগুলো আছে
Oil tanker.
ট্রাকে আর কি ইয়ে করা, ইয়েস, অয়েল ট্যাঙ্কার বা সামথিং।
Okay.
তা এখানে যখন ট্যাঙ্কারের ভিতরে ফ্লুইডও আছে,
Yes.
হ্যাঁ, তো তখন আমার যখন স্ট্রেসটা বের করতেছি, ইকুয়েশন জেনারেট করতেছি, সো ফ্লুইডের এই যে ওয়েট, এরপরে তার ফ্রিকশন, এরপরে হাইড্রোস্ট্যাটিক ফোর্স যেটা ওই ভেসেলের উপরে ইয়ে করতেছে, অ্যাক্টিং করতেছে, ওগুলো আমার কাউন্ট করা লাগবে না?
Okay, on second. What is your ID? Is section B or
18.
section A? Your section A, right?
Yes.
Section A. Your ID
18.
8.
18.
Tell me the full ID.
18020801.
1802080018. 18. Okay, good. You asked a very good question. That how you will figure out. You see in the assumption what we make assumption that inside the pressure vessel experience a uniform pressure B P, right? That means we are thinking about not a moving body, a static body that has a pressure inside P. And you talking about that one, say Oxygen Bangladesh Oxygen Limited, they carry might be liquid oxygen inside, right? So you carrying liquid oxygen initially in a truck, when it is moving, velocity 0. And start to moving, it accelerate, say within say 40 seconds from 0 to 60 miles per hour. So what will be fluid in the inside? It will move. It will not. It will create some extra pressure at the end of the your cylinder. Okay. Give you example. I was working in a airplane 747-8 of Sultan of Brunei. Okay, we install 2 water tank in the aircraft. Okay, so you think that water tank, say he's flying from Brunei to Kuwait, and both water tank is half. Okay, so when he land, then what will happen? The speed of the aircraft will from certain to 0, right?
Yes, sir.
Second, let me share with you because your question is interesting. So you have a pressure vessel like this kind of cap, right? It's half full. So airplane is moving at the high speed. So suddenly it's taking off on the ground. Then over here speed is 0. So all the fluid is still moving. Then your fluid level will be this kind. Then pressure this side will be low and this side will be high. So this situation we are working with a dynamic body, right? But we derive the equation for experiencing uniform pressure. We are not considering the dynamics of the fluid, the acceleration. But if you work in this type of project, then you need to consider the dynamics, that due to the certain speed up or certain brake of the vehicle, what will be effect of the fluid. There is some mechanism is called, this type of load is called sloshing load, SLO. I'm trying to read SSING, sloshing load. Okay, so we need to figure out the sloshing load of the fuel. And you see, if fluid height become high like that, all the fluid pressure will work in the cap, and you need to make sure this cap is not breakdown, is not fail. So there is a different way. It's called baffle. If you use the baffle inside, that means if I put multiple discs with some hole or porous discs, then fluid will try to go to the forward section, but it will move slowly. And this height of the level, I might to keep it almost constant. It don't matter. You speed up your vehicle and you stop your vehicle. Okay, so you have your answer? Hello?
Yes, sir. Thank you.
Okay, so we can stop it here.
Yes, sir.
I need to keep parallel with your other section. Okay, so thank you very much. We are keeping here. Okay. Okay, and have a good
Sir,
day. Yes.
there is a question, sir.
Yeah.
Sir, is there any radial stress working along this thick wall
Yes, thick wall. When you derive the thick wall, we need to consider all three stress: sigma T, sigma R, and sigma L. But in
So will
both
it be
cases,
sir I mean is the radial stress tensile or compressive?
it depends where the pressure. If pressure is inside, obviously it is tension because it's pushing outward direction. If you have pressure only outside, then try to squeeze, then it will be compression. A pressure vessel, it don't mean that you have pressure only in the inside. Sometimes you have pressure might be only outside. For submarine, a getting bottom of sea 2 mile, how much will be fluid pressure? All the P equal to H rho g, right? ITC in the fluid mechanics. So what outer surface will be experienced pressure. But inside of the submarine, there will be only people. How much people can survive? You have to keep pressure close to the atmospheric pressure. But outside, there might be huge pressure. So it don't mean that the pressure will be only inside. Okay?
Yes, sir.
So
Thank you, sir.
your radial stress might be compressive or might be inside. Okay, thank you very much. So what is your ID? You asked about your
Sir, 91, sir.
91. Okay. Okay, good. I always appreciate for asking questions. Okay, so we are keeping over here and have a good day. Bye.
Thank you, sir. Assalamu alaikum.
Walaikum.